Thank you, I would say. Thanks for the introduction. I will kick off. So my name is Depover. I'm from Ghent University, and today I will mainly present the work of our PhD student Simon, so he deserves the credit for what will be presented today. This is also in collaboration with the group of MCL, Material Center Leoben, who are mainly responsible for the numerical interpretation of the TDS and permeation data. I will not focus too much on their results. This will come later in the publication. But basically, I will talk about the interaction of hydrogen with retained austenite, because it's quite specific and quite interesting to take a further look into that. And two type of automotive steels, drip steel and quenching and partitioning steels. So let's take a look why these are important. Well, we go in the banana-shaped curve, as you can see here. We want to go to the upper right corner. Higher strength levels, higher ductilities, because then we can thin the plates, we can have some weight reduction. This is good for the CO2 emissions. So TRIP and QMP, they are here. They are very interesting, and they come with a specific heat treatment. I will not go into full details, but for the TRIP heat treatment, we stabilize austenite so it's stable at room temperature, so we can take advantage of the TRIP effect during mechanical testing. For QMP, this is different, but QMP, we can go to intercritical annealing or above the AC3 temperature if you want a fully martensitic matrix. In our case, we went in between AC1 and AC3, intercritical, to have some ferrite and austenite there. And you quench first here, and then we do also a partitioning step to make sure that the carbon can segregate to the austenite to stabilize it further, to have a stable, metastable retained austenite at room temperature. The alloying elements, this is quite lean, quite simple in chemical composition. We have some carbon, we have some manganese. Solubility of both elements are larger in FCC. So this makes sure that we can move the pearlitic and benitic nodes to the right, so that we don't form pearlite or bainite in the microstructure, because we want to have some pearlitic microstructure with some martensite and then some retained austenite present. We also add some aluminium and silicon because you want to avoid carbide formation, because you need your carbon. You need your carbon to stabilize the retained austenite at room temperature. Then you can take advantage of the TRIP effect. Similarly as in TRIP steel. Well, in the end, we have this typical microstructure. As you can see here, we have ferrite because we don't go above AC3. If you go above, you have a fully martensitic microstructure. Then we have two types of austenite. We have blocky austenite, quite large ones. And then we also have some filmy austenite inside the martensitic grains, as you can see. So this is a bit more complex, because in TRIP steels you only have the blocky, bulky austenite present. And this is due to the partitioning step happening here. Okay, this is in a nutshell. So if we take a look to the characterization, this is the TRIP steel. So we have a ferritic matrix, some retained austenite, some bainite, some martensite present in the material. If you take a look to the phase map based on EBSD, you can see quite a lot of green. Green is the FCC, the retained austenite, which is about 9.6%. You can see also a bit of black. This is due to the martensite, which is less easy to index, of course. So this is the TRIP steel. We have some retained austenite present, about 10% blocky, and this is possible to characterize by EBSD because it's quite large. This is different for QMP. In QMP, we also have the BCC and FCC, so we had ferrite, as was introduced before by the heat treatment. And then we also have some filmy austenite. Filmy austenite is about 100 nanometers, so it's very tiny. And EBSD cannot capture all the retained austenite present in the microstructure, because it's a surface technique. What we mainly can see here in green, we see retained austenite. This is the bulky, blocky austenite. But we also have then the ferrite. So this is a superposition of the image quality map with the phase map. So you can see in bright red, you can see the ferrite, and then we also have with higher dislocation density the martensite. So basically, based on EBSD, we have 7.7% of austenite. But if you do XRD, then you can see that we have a higher fraction of retained austenite. The difference between both is the contribution of the filmy austenite, because it cannot be captured by EBSD, but it can be captured by XRD. So basically, by this division, you know how much filmy austenite you have present. For the TRIP steel, this was about 9.6%, and this was all the blocky one. And then if we do here XRD on these materials, you have the same amount of retained austenite present. So this is the characterization of the materials. Let's go a bit further. Well, we have the benefits of TRIP. Why? Because it can give you additional plasticity, because of upon deformation, you have transformation of retained austenite to martensite. This is BID. However, you can also take a look at the hydrogen characteristics, because retained austenite, FCC, has high solubility for hydrogen, low diffusivity, so it can be seen perhaps as a deep trapping site. Maybe that's interesting, because if you have some carbide addition, for instance, this can turn irreversible trapping. This can be interesting to improve the resistance against hydrogen embrittlement. However, upon deformation, that retained austenite transforms into martensite, fresh martensite, which is quite brittle, and it can also initiate your fracture. In very early work, about 10 years ago, we compared different automotive steels. You can see here TDS profile, but at the high temperature, it's very tiny, but we had some presence of retained austenite that trapped hydrogen. We proved this by applying cold deformation, and then the peak decreased. So if we applied cold deformation, your retained austenite vanishes, and also this peak vanishes. This is because of processing this amount of hydrogen at retained austenite. If we charge this sample without mechanical load, there is no additional trapping at retained austenites. So this is quite interesting. But from processing, we had some hydrogen present at retained austenite. This is for TRIP. Let's now take a look to QMP. So for QMP, we do first saturation curve, because if you want to do correct TDS evaluation, you need to know that you have a homogeneous distribution of hydrogen in your microstructure. So at about 2 hours, we have full saturation, as you can see here, 7.5 weight ppm. And if we then do TDS testing, you can see that we have, with different applied heating rates, you only have low temperature peaks. So taking a sample, charging it with hydrogen, doing TDS is not yielding any high temperature peak if you just put the sample as such. So retained austenite is not able to trap, while the amount of time that was given is sufficient enough, because we have small islands, and if you calculate with the diffusion coefficient how much time we need to charge or to saturate retained austenite, this is sufficient, the 2 hours. This is of course different with duplex stainless steels in 304, then you need much more longer time for charging to be sure that you can charge the austenite in the material. So no high temperature peak, nothing trapped at retained austenite when you do just the charging. Let's now take a look to the mechanical performance. So in the TRIP steel, remember, we had some high temperature peak linked from the processing. And if we then do mechanical testing, and this was done in the PhD of Aurélie, which is also present today, you can see that crack initiation nicely starts at the interface between martensite and the matrix. So this is basically the retained austenite contains hydrogen. Upon deformation, it transforms to fresh martensite, which is a brittle phase. The concentration at retained austenite is quite high solubility, but then it comes into the fresh martensite, which cannot take all that hydrogen. It's supersaturated with hydrogen that starts cracking. Crack initiation at that retained austenite that transformed to martensite. You can also see it here, and here as well you can see here there's a retained austenite that has transformed to martensite. Crack initiation brittle, because we're dealing with fresh martensite, but then we have crack propagation in ferrite, which can be crack arresting, which was also then nicely shown yesterday in the talk of Professor Koyama with HCP then. So here we see the different type of ferrite that can happen. So this is when hydrogen is present at retained austenite, then upon deformation it can be quite detrimental. So it's not a deep trapping site that you want in your material if it's charged upon mechanical loading. Good. During my postdoc, I also went to NTNU to work with Afous Bernouche, that you might know, and then they have this in situ micromechanical testing. And the very nice thing is that you can do micromechanical testing, but also evaluate with SEM EBSD what is happening on your surface. So you can evaluate deformation mechanisms during mechanical loading in the presence of hydrogen. Because you can do this in vacuum, just in the SEM chamber, in vacuum then without presence of hydrogen, but you can also add some plasma charging there. Plasma charging can then, during mechanical loading, interact with your surface, can be uptaken by the microstructure, and can have an effect on deformation mechanisms. So if we now interrupt, so we do a tensile test, but then we interrupt it at 20% of strain, and we take a look to the microstructure, then you can see with this EBSD phase maps, and I hope it's visible, in the case of uncharged, so without plasma charging, you still see quite a lot of green of austenite present, while the percentage of green is much less when we have plasma charging. So hydrogen, the idea is that hydrogen was present at retained austenite because of the plasma charging, in situ charging with mechanical loading. That hydrogen then reduces the stacking fault energy of the retained austenite, and your transformation to martensite happens faster in the presence of hydrogen. This is also shown in duplex stainless steels and 304 stainless steels, that if we do charging with hydrogen and we interrupt the tensile test, that you reduce the stacking fault energy and that you have different deformation mechanisms acting. For instance, you can see deformation of epsilon martensite sooner in the case when hydrogen is present compared to the uncharged condition. To prove that this is linked to the retained austenite, I also took that sample at 20% of strain. I take it out, I go to TDS to take a look at that high temperature peak. Remember, because there we have some interaction with retained austenite and hydrogen. And if you then take a look, indeed in the uncharged condition we still had some. In the beginning we had quite a lot, but then at 20% of strain you lose, but you still have quite some hydrogen trapped at retained austenite. But in the plasma charged condition you have less. So you had accelerated deformation in the case when you had plasma charging because of the presence of hydrogen at retained austenite. Okay? So then we continue and we want to know how is this retained austenite trapping. Quite difficult to evaluate with TDS. I will explain later why. But another technique to evaluate hydrogen characteristics is permeation, electrochemical permeation experiments. I will not explain this totally to you because basically you know at the entry site we have cathodic charging. We introduce atoms of hydrogen, they can diffuse to the lattice. At the anodic sites we have oxidation of hydrogen, and basically based on that curve you can determine the diffusion coefficient based on Fick's second law. For this first investigation we did not use TRIP or QMP because upon loading we have transformation, right? So we used dual phase steel ferrite martensite. Quite straightforward microstructure, quite easy. And it's not only that we did permeation, but we also applied constant mechanical loading to our sample. So I have this proof ring, this constant load proof ring, that we can have surrounding a rectangular sample, and then we can apply an elastic or plastic load to that sample. And we can evaluate the role of the load on the diffusion of an atom of hydrogen through your lattice. So then let's take a look to the results on this material. So first, this is for the dual phase steel. Here you can see the apparent diffusion coefficient. First, when you do elastic loading, 60–80%, we see an increase of the diffusion coefficient. This is because we increase the lattice and hydrogen has more space to travel. So we have faster diffusion. This is something that should be introduced also in numerical interpretations as well, because your diffusion coefficient is not only dependent on the stress, but also the stress and the hydrostatic stress that you can model with finite element modeling, but also your diffusion coefficient is depending on the microstructure that is changing during a tensile test. So with the elastic loads, we have an increased, how many minutes do we have more? 10. Okay, then I'll slow down. Good. So with elastic loading, we have an increased diffusion coefficient, expansion of the lattice, so that's fine. At 100% of the yield strength, and this was determined by the 0.2 offset method, we had again a reduction of diffusion coefficient. Of course, at 100% of yield strength, you have microplasticity. So at that load, you already introduce the nucleation of new dislocations, new defects that can trap hydrogen, that can slow down again the diffusion. This is what can be seen here when we go to 100% of load. Let's continue further because we can also apply a plastic load to have more dislocation generation and more trapping sites, so you increase basically the trap density in your material. So if we increase and we go to 120, 140, we can see it indeed. So at 0% we have more or less the same diffusion coefficient as at 100. So here basically there's a compensation between the elastic stress and the plastic stress. But if we continue further and we have more dislocations, more defects, we slow down and your diffusion coefficient is dropping. However, this is during constant load. So for these situations you have both, because it's constant load and then you do permeation, you have the contribution of the elastic stress, but also the plastic stress. Both act at the same time. So to prove our point that the elastic stress is indeed accelerating diffusion, we also did the same. So this is just a repetition, elastic and then plastic. Plastic we decrease, but we also took the 120 sample, 120 constant load, so we have elastic contribution, plastic contribution. After that 120, we also release the load. And then your elastic is recovered, right? And the only contribution is only the plastic. And then you can see, indeed, that you drop a bit more. The diffusion coefficient drops a bit more because your contribution of the elastic part is gone. And this is a proof, indeed, that the elastic strain can increase the diffusion coefficient in these materials. Quite simple materials, dual phase, ferritic, martensitic. Let's now go to QMP because we want to evaluate if retained austenite can trap We don't know yet, because with just charging, we don't see a high temperature peak. So at 0% of the yield strength, we have this permeation transient. Now with elastic load in dual phase, we have an accelerated diffusion, right? With QMP, we slow down diffusion. Quite strange, the opposite as in the dual phase deal. So let's continue. Is this now an error or not? Well, with 75, we decrease it more. 100, 125. So basically, you see that diffusion coefficient drops, and the elastic contribution is slowing down your diffusion. So this is the ID. What is the only difference? Well, we have some metastable austenite in QMP, and perhaps that austenite can trap upon loading, which is not possible without mechanical load. What we did then is to see, because you have the subsurface concentration that you can measure based on the current density that you can obtain during permeation testing. But if you want to know the concentration, you can do subsequent to the permeation and the load. We can take the sample and we can go to TDS, and we can measure the concentration of hydrogen. So if we take these samples after loading during permeation, so hydrogen has passed through it, and we see an effect on diffusion, we take those samples and we go to TDS. And as you know, in the beginning we had no high temperature peak. Neglect this low temperature peak because there is quite some time in between the permeation testing and then the TDS testing, so you have a fusion of hydrogen, so this first peak doesn't really tell anything, but the high temperature peak is very stable, so it will stay there. We also verified that by waiting different times. So 0%, no high temperature peak, the same as just with charging. But then we do loading, and you can see suddenly with 50% of yield strength, we had a high temperature peak. 75% even more, 100, 125. So suddenly, upon loading, the retained austenite is capable of trapping hydrogen. And this is interesting because this can explain why we see crack initiation at retained austenite, also in QMP. This has not been seen before, that retained austenite in QMP can trap upon mechanical loading. To prove that this is attributed to retained austenite, we need some characterization by the microstructure, of course, because what is happening here? Is it detrapping from a trapping site, or is something else happening? So we did some differential scanning calorimetry, and you can see here the heat flux. So basically, you can see phase transformation during this type of measurements. You can see exothermic and endothermic reactions, and the blue one is with pre-strain. So here we can see a continuous, because it's below zero, a continuous endothermic reaction, which is basically linked to the relaxation of the internal stresses, because you have done some pre-strain to the material. And you have different regimes, and this DSC measurement. The first one is basically clustering of carbon atoms at that temperature, which is a prerequisite for the precipitation of transition carbides that is then happening in phase 2. And then in phase 3 and 4, we have indeed your decomposition of austenite. So basically your retained austenite at these temperatures will decompose, they will turn into BCC again. And because they are gone, because the trapping site is gone, because you have decomposition of retained austenite, of course your hydrogen trapped at that retained austenite comes a BCC phase, and then you can see this peak at the same temperature regime as you can see here in DSC, so it's linked to the phase transformation. At the very end in 5, you also have cementite precipitation. Another technique to further validate, but I think this is already sufficient enough to claim that this high temperature peak is linked to retained austenite. We also did some high temperature XRD, because with XRD you can also evaluate the FCC and BCC contribution. Yes, very good. So here you can see that the FCC peak, so you see continuous shift to the left because of thermal relaxation during the test. But you can also see that indeed the FCC peak is vanishing at that temperature. Then here we have ferrite, and here you have the onset of, again, austenitization, right? So this comes at the same temperature. If you take a look here, this is around 450 that you have your decomposition of retained austenite. Here we have it about 450. Here we have it about 470, so there is 20 degrees of difference. Well, that can be explained because of the temperature is captured at the surface, but your detection of hydrogens in the detector is 1 minute in between, because it has to travel to the detector. 1 minute is also 20 degrees. So it's exactly the same. So this coincides very, very well. So upon loading, we're able to charge retained austenite. Okay, hypothesis. I will end with a hypothesis. Well, what we think that is happening, upon mechanical loading, there are defects present. The defects don't trap without loading. With loading, they can trap. So what is possible is that the defects are occupied by carbon, for instance, and that upon loading, carbon is released from the defects, and that hydrogen can be trapped at those defects. And then we have that high temperature peak. This is the first hypothesis. Second hypothesis is during mechanical loading and hydrogen, we have a defectant concept acting Kirchheim's theory, and that we have additional generation of defects, vacancies or dislocations. So your trap density is basically increasing, and that's why you have a high temperature peak. So these are two hypotheses, and very fresh results are now available on trip steel. And trip steel also permeation under load. We go with trip steel, same retained austenite, and then we take a look to the high temperature peak, and it's all the same. So if we do elastic plastic loading and we take a look to the high temperature peak, there is no increase of that peak. So this makes us think that the first hypothesis is the one which is acting because your carbon segregation is happening at partitioning. So at QMP you have carbon segregation, and this is then in competition with your hydrogen trapping. So your trapping sites are occupied by the carbon. And this is based on these comparisons that we can conclude that. In the future, we want to conduct some APT to prove that the local chemistry at the interface is responsible for the trapping. This is complemented with numerical research by MCL to evaluate the deep trapping, because basically we see decomposition here. So Kissinger's equation to calculate the desorption activation energy is not possible, because you just see the peak because of decomposition of the trapping site, not because of detrapping of hydrogen from that defect. So this is why they help in numerical interpretation of trapping at retained austenite, but I will not give further details to that. Thank you.